Welcome again to the NP12 course on storage systems. Today we will take a brief look at some aspects of performance modeling of storage systems. We've been talking about how storage is often the slowest component, okay, and we looked at disks and the more faster variety SSDs or flash, and the future what is called phase change memory, PCM, etc. Right? We didn't really study PCM, but these are considered the future type of non-volatile storage memories. And when we are designing any large system, it turns out the slowest component determines the overall speed of the system. Okay. In our case, the slowest part is the disk or the storage system, and so it turns out that it's a slightly good thing for us, because oftentimes if something is really slow, that drives everything. So the analysis can be somewhat simpler. Okay. So oftentimes in a storage system kind of situations, you do what is called back of the envelope calculations, right? A good example is if somebody says I have a disk and it can only do any random access about 10 milliseconds max, okay, that they cannot do anything better than that. That itself will tell you that there is no way in the system you can do more than 100 transactions per second, assuming that the transaction CPU processing is within milliseconds, okay, sub millisecond, okay. That itself will tell you that the disk, since it is the slowest part, it will limit the speed of the whole thing, and you can easily say without any hesitation, without doing any complicated analysis, you can just say very easily that you have to, let us say at the most say that you can handle 100 transactions. If somebody says 100 is too slow, give me 200, then you say go and get 2 disks, okay. So again, as long as the processing speed is reasonably fast, that will take care of it, okay. Of course, you can go only so much, because finally those systems also will start, other systems also will start becoming bottlenecks. So what I just want to mention is that oftentimes simple modeling is very useful in this area, okay, because of this wide disparity in the speed, okay. And the other thing about this system is that oftentimes because of the slowness of the system, you use caching, etc. Okay. Caching, buffering, all these things are widely used in storage systems, and sometimes it so turns out either because of a bug in the system, the caching might have to be disabled, or because of the workload, the caching does not work very well, okay. In which case what happens is suddenly you will start seeing that all the optimizations that you assume with respect to caching no longer work, and you will find that your system is really crawling, okay, really crawling, okay. And that is because the wide disparity in the cache speeds and the disk speeds. If the caching somehow is off, you get into serious problem. And this happened quite regularly, or I shouldn't say regularly, it happened on and off. Sometimes you might have heard about, there was some time back a problem with Facebook, where because of some errors, some important cache was turned off, because the error processing or error management systems, they shut off the caching for some time, okay. And the minute the caching is turned off, what will happen is that it has to go through, everything has to be picked up from disk, and since disk is so slow compared to memory, that means that it was barely able to do the processing, let us say barely even less than 1% of its older capacity. If you are doing as low as 1% of the previous capacity, that means what will happen? The requests are coming in as usual as before, right? The queues build up like anything. Once the queues build up like anything, the system looks completely hung, okay. There is no chance of your being able to do anything. Everybody looks as though nobody is able to get any service done. And I think this also is probably you might have heard about it. If you want to get a appointment for the passport, right? You have to get some appointments, and it's a totally big lottery, right? You have to get it in a small window, everybody is trying to access at the same time, and most likely it's a disk limited system. I'm not very clear why that's the case, okay. So basically you can barely get in and almost nobody is able to get through, right? System looks completely overloaded, okay. That's basically because somehow the transactions, right, you are unable to do fast enough, okay, and caching or something is not useful, or it is a database kind of system where by definition you are accessing randomly various parts of the disk, okay, where caching will not be useful, okay. So so you'll find that we are hit with this kind of phenomenon anytime you make a transition from memory to disk, for example, okay. And the reason why systems like Google etc. work very well is because they are very, very clear about this part, and they ensure that the most important things are always in memory, okay. And but as I mentioned, sometimes there are errors like Facebook suffered. They also try to do the same thing, but errors prevent the caches being used, because somehow the information is somehow invalid. Some part of the subsystem has decided that the information in the cache is invalid, okay. Once you say that it is invalid, then you are forced to go to the more let us say trusted part of the data, and if it is on the disk, then again the system is going to just crash, because there is no way the disk is going to be able to service it, okay. So these kind of things happen. So it's useful to think about let us say what is going to be the worst situation for you if you are using this kind of system, so that if you can tell people I cannot do better than this in case some bad things happens, okay, so that you can start putting that into your models. Again, if you are thinking about storage system, there are various aspects that come into picture. Again, we looked at device drivers. There is some processing going on, right? You can interrupts and whatnot, right? But in addition, that's what IO completion, processing, and interrupt handling. Okay? This is something which you are already aware of, and if you have lots of disks, you will have lots of these things, okay. And since you are also doing storage across networks, there is also a network packet processing that can come in, and at a very high speed networks like gigabit Ethernet etc., they can be pumping packets at high rate, because they are working at gigabit speeds, and Ethernet typically is at 1500 bytes or 9000 bytes, what I call jumbo frames. At gigabit, they are actually able to pump it at very small intervals of time, okay, microseconds, okay. So if you are able to pump at microsecond level, if you send huge numbers of them, okay, then every time you process the interrupt, okay, it might take so much amount of time. It actually causes what is called cache pollution, because it displaces the previously cached information, etc., right. Therefore, what happens is that this interrupt handling, network processing, etc., can create a lot of disturbance in the system, and they essentially cause lot more cache misses of the CPU, etc., and things will be taking much longer than expected, okay. So there is a lot of, oftentimes in very high end storage systems, there is dedicated hardware for interrupt handling and network packet processing. The simplest thing of course is what we already discussed, what is called host bus adapters. Host bus adapters are those proxies for the CPU which will handle all this business about interrupt handling. They are the people who do, just like in the networks, you have something called segmentation and reassembly, SAR. There is a similar thing in storage systems which do SAR and also interrupt handling. These are called host bus adapters, okay. They are essentially used to shield the CPU from all this interrupt activity, okay. In addition to these things, you will notice that CPU utilization is also required for processing storage requests in many situations, like in suppose you use compression, you have to decompress it, do encryption, you have to decrypt it. This can also be quite costly if done in software. That's why you will see very high end equipment, they will not do encryption, decryption in software, they will do it in hardware itself, okay. And there is also something called deduplication. For example, the idea is that oftentimes there are a lot of copies of the same object going around. Well, I think we already discussed, I think once, you have mail object for example, which is I want to send a document to somebody. There is a document in my file system, but I am also sending the copy, and I keep a copy of the mail I sent. Then there will be a copy of that same document in my sent message, right. So now 2 copies are there. Okay. So it turns out that there will be a lot of copies building up because of various aspects from the application point of view, and you want to find a way of keeping only a single copy or as many copies as required to ensure that your error management is handled properly. For example, if somebody decides that because I can suffer failures of sectors and all those things, if I keep 2 copies, if one goes bad, other guy can use it. So you might have a minimum. I just want to have exactly not more than 2 copies or 3 copies. Okay. So whereas if you don't do this deduplication, the number of copies can be unlimited. For example, I work with a student, I give a copy to one particular paper, next year another student comes around, I mail it to him also, another student comes around, I mail another copy. So my copies can just keep on building up, okay, in my sent messages. Okay. So the deduplication is a technique by which you try to reduce the let us say the number of copies in the system, but that means that anytime there is an object, I need to be able to figure out if the object exists in the system or not. Okay. Now that's a non-trivial object. Okay. It's something like, again, it's a search, you're searching on your own disk essentially, and you know that disk is very slow, therefore how do you search when you have terabytes of, because nowadays we have 2 terabyte and 3 terabyte and 4 terabyte disk, how do I search given that I'm trying to do something, some activity, I instantaneously should see if there is a copy that I'm generating. Anytime a copy is being generated, I should see if it is already there, right, and then say that okay, don't make a copy like that, put a pointer to the already existing data. Okay. So the deduplication can be very heavy with respect to processing. Okay. So there are all these kind of things that come into picture. Again, if you are doing a distributed search, for example, like what Google is doing, right, you might want to have some performance model for multiple nodes doing something together. Okay. So given this simple background, it turns out if you think about it, there are various models of performance. I am just going to talk the most simple varieties. Normally, as I mentioned, what is called back of the envelope calculations are reasonably good for fairly simple storage systems. You don't need really complicated models. Okay. So you can do this back of the envelope calculations, and usually you essentially figure out what is called the bottleneck device. You find out what is the bottleneck, and that will drive everything else. Okay. If something is a bottleneck, nobody else can go faster than that particular bottleneck, right. So you look at how fast that bottleneck device is doing something, that will decide everything else. Okay. So this is what is called bottleneck analysis. Okay. So it turns out there are 2 main types of there are many more, but I am just giving you here some just for simplicity. What I call operational models. Here they make very limited assumptions, and then you have slightly more detailed models where you assume certain distributions. Okay. And usually you assume these distributions to be mathematically tractable. So queuing theory is a good example of this. There are many types, but I am just in this particular talk I will just mention these 2. Okay. So we will just quickly take a look at each of these things and see how they can help us. A good example of an operational law is what is called Little's laws. Okay. So usually if the arrivals and completions are just about equal during some observed period, then this Little's laws usually are quite accurate. Okay. So let us just see how this works. Suppose there is a particular job and it spends, J is the time that is spent in the system. Okay. So since we have n jobs, the mean time spent in system is J by n. Okay. Basically this is the time in the system, there are n jobs, therefore the time for each job is J by n. Again you can see mean number in system is J by T. Okay. And you can easily write it as J into n into n into T. Okay. It's very simple. This I am just doing simple algebraic manipulation. It is just you see n and n cancel, therefore it is same as J by T. But J by n is what? Number of, it is the time taken divided by number of jobs in the system, that is response time. Okay. What is n by T? It is the number of jobs divided by time. Okay. Now this basically is the throughput. So essentially the mean number in the system is basically response time into throughput. This is an example of a extremely simple analysis will tell you that under these kind of conditions, okay, this will be true. Or you can oftentimes written as the mean number of customers in a queue for device I, the mean number, okay, the queue size at device I will be same as xi into Ri, where xi is the response time and Ri is the throughput. This is the, sorry, I made a mistake, throughput is xi and response is Ri, okay. So throughput is what? Basically number of jobs per second, and response time is how long you take. Oftentimes this is written also as L equal to lambda W, where L is the mean number in the system and lambda is the arrival rate and W is the mean time spent in system, okay. You can see here it is talking about response time, here it is talking about arrival rate. Basically if you are in a stable situation, reasonably stable situation, which is basically arrivals approximately completions, then response time and arrival rate, basically there is some correspondence between these two, okay. If your arrival rate and the way the jobs are departing system are highly unbalanced, then you will start seeing big queues developing, okay. As long as you are not in that really pathological situation, right, then it turns out that there is a correspondence, there is these two are essentially equivalent, okay. So oftentimes you can, if you are in a slightly stable kind of situations, right, without any assumptions about distributions, this particular rule is often applicable. Of course, there is something you have to be careful about. When you look at the systems, you have to make sure that the assumptions of some of these laws are valid. Luckily for us, Little's law is valid in many different contexts, okay. It does not have very few restrictions it has got, okay. But generally whatever I am talking about today, you have to be careful about the assumptions, okay. Make sure that the assumptions are valid, then many simple rules of this kind can be done, okay. So basically what we are saying, again just to repeat, the queue size in front of device I, there could be a lot of devices in the system, is given by the throughput of the device multiplied by the response time for a job at that particular device, okay. That is to see how big the thing is, okay. So again you have to spend some time thinking about it. Some of them look a bit non-intuitive, but if you think carefully and look at especially this kind of thing, you will see that it is fairly straightforward to derive, okay. Oftentimes we assume what are called Poisson arrivals. I will not go too much into details, but basically essentially it means that there is a rate at which it is coming and every arrival is independent of the previous one, okay. There is no correlation, okay. And if you take a small interval, okay, the arrival rate is lambda, so in that small interval lambda and lambda star delta, okay. And if you take a small interval delta, probability of more than one arrival is negligible, okay. So basically arrivals in non-overlapping intervals statistically independent, okay. You take any two non-overlapping intervals, then the arrivals are statistically independent. There is absolutely no information flow from this interval to this interval or vice versa, okay, independent, completely independent, okay, oftentimes called memoryless, okay. So the expected arrival time, because if lambda is arrival rate, expected arrival time is 1 by lambda, okay. And you can, the probability of an arrival in time t given this Poisson can be derived as 1 minus exponent, I am not going to go into it, but basically 1 minus exponential of minus lambda t. Therefore no arrival is exponential minus lambda t. And you can also derive probability of k arrivals in time t is basically same as this, but lambda t to the power of k divided by factorial k, okay. So I am not going to go into too much as detail, but generally Poisson arrivals are assumed, and similarly you can also, basically because you have this independence of non-overlapping intervals, okay, and that simplifies analysis. Similarly you can think about departures also, okay. So what we are looking for is the following. Suppose I want to analyze some of this kind of situations. There is one single big queue, and from this queue, okay, I have CPUs here, CPU 1, 2, 3, 4, and people are coming at arrival rate lambda, okay, and the service rate is mu, everybody, okay, CPUs. The second thing is, suppose the other possibility is I have a queue here, and what I do is I have 4 subsidiary queues, okay, and I put one processing there. Okay, okay, I think I can avoid this. Basically, in some sense, we will remove this part. Okay, it's not necessary. Okay, so somehow basically instead of lambda, I have lambda by 4. Let us say. Okay, so this 1, 2, 3, 4. Okay, again this is doing at me. Okay, now the question for us is which one is better? Okay, is the left one better or the right one better? You will often see this in practice. For example, you go to railway reservation counters. In some places, you will find that there is one central queue, and then from there you go to various things. Okay, there will be some, let us say, electronic indicator which says as soon as you get in, you get some number, and then you all sit in one common area, and then you will get an electronic and saying this number, go there. Okay, and you will figure out which of this, and will tell you where to go also. Okay, that is this model. The other model, which is much more common because it requires less of infrastructure, somebody comes in, he looks which is the one which is most likely available, he goes there, right. The question for us, which is better, is this better or this better? Here basically the idea is that there are 4 independent queues, and then once you get in, you cannot go to any other queue. Of course, real systems, people do all that also. They go into this and then decide this is moving faster and they move all those things. But let us say for this particular problem, we do not do that. The question is which is better. Okay, this turns out to be what is called m/m/4, and this is 4 into m/m/1. Okay, I will tell you what these are. Okay, these are 2 types of models of systems, and here you will see that there is a total processing power of single queue is feeding 4 of these things, whereas here each of them is separate. Okay, there is essentially 4 units of processing power for the queue. That's why it is 4. Here it is 1 unit of power is per each one. That's why MM1. Okay, I'm sorry, there was a slide here, but somehow it. Question is which one is better? It turns out if you do it carefully, this is what you get. Okay, I just want to check whether, yeah, let's see. Okay. You will see that if you look at average response time and utilization, if you do analysis, then MM4 will be always better than 4 into MM1. Okay, and you can see why also, basically because in practice also you will notice that if you look at this, it is because if for some sudden reason there is one job which takes too long, right, people are behind this particular queue, they are stuck. Okay, whereas if you are here, if a particular job takes too long, right, you are going to be, you still have opportunities to go here because this guy is taking too long. Okay, but the guy who is not stuck because he can still go to any of these guys, because he still get a chance of being serviced by any of these guys, whereas here you get stuck. So if it turns out an average, this has a implication with respect to what is the typical waiting time for somebody to be served in this queue versus this one. Okay, normally the idea is that your serving capacity should be as far as possible aggregated together, as far as possible. Don't split it into pieces. But a good thing about splitting into pieces is that you get sometimes dedicated processing power. Here basically happening is that I have to share all this across all these guys. Sometimes you are in a situation where you want this particular thing. Okay, you want it, and once you get it, you want to hold on to it. There are situations that happens where this kind of thing model might be better also, but especially for guys who have long let's say requirements, okay, for processing. Okay, anyway, so the question for us is how do we do these things? Okay, so I'll just show you simple MM1, and then I will not do MM4, I'll do MM, I'll just mention the result for MM2 and show that there is some, how you can compare these things. Okay, if you have a MM1 system, okay, think I seem to be missing out some things. 2 or 3 slides are missing. Okay, sorry. Yeah. So basically what's happening is that I have certain arrivals, okay, people who are looking for service, and then there is some service. Okay. Now the arrival rate is lambda and the rate at which I am able to service is mu. Okay. Now what we are looking for is how many consumers, how many customers are there in the system. Either you have customers 0 number, nobody is there, 1, 2, 3, I minus 1 or I plus 1 or n. Okay. So if I am at I minus 1 customers, if a new customer comes, that is arrival, I go to this state. Okay. If there are I customers in the system and one service gets completed, okay, I go to I minus 1. Okay. Now we can see that if the arrival rate is much bigger than the service rate, then queues will build up. Okay, it's unstable situation. Whereas if the arrival rate is smaller than the service rate, okay, then there will be some queues because of stochasticity. Okay, there will be some queues building up now and then, but they will get flushed out. Okay. So if lambda is less than mu, then you can get a steady state, and basically you can compute a steady state as follows. Okay. What I am interested in is finding out the probability that I am in this particular state, that is with I minus 1 customers in the system or I plus 1 or whatever. I want to be able to compute the probabilities. Okay. So if I am interested, what I can do is, let us say that I call the probability of being in this state pi of I, this is pi of I minus 1. So now from here I go with at rate lambda, from here to here I come with rate mu. So if something is stable at each point, suppose I draw a line like this, if it is the situation is the system is stable, the rate which I am going from this to this or from this to this should be constant, should be the same. Therefore, they will again be the probabilities will be stationary, they will be at the same, they will not change. Okay. So basically the probability that I am here is pi I minus 1 and multiply that with lambda, that should be equal to the number of guys who are here or the probability of the system, right, being here multiplied by mu. That is basically what it is. So basically I take, if n is the number of guys, pi I minus 1 is the probability of being in that one, then when n into pi I minus 1 is the number of guys here, this will be pi of I into n. So basically you can see that this equation has to be valid. N into pi I minus 1 into lambda should be equal to n into pi I into mu. So that is the number of guys here, the chances of anybody making a transaction is lambda, the chance of anybody making a transaction is this. Okay. Or you can just look at from the point of view probabilities, pi of I minus 1 going to this into lambda is this, that should be same as this part. Okay. Pi of I and job getting finished, and that is pi of I is equal to lambda by mu, which is rho. Okay, this is called utilization, lambda by mu, and lambda by mu is basically less than 1, because I am assuming lambda less than mu, lambda by mu will be less than 1. So pi of I equal to rho of pi of I minus 1, and this is true for pi of starting with I equal to 1, 2, etc. Okay. Is this, hopefully this is clear. Okay. So it turns out from this you can compute pi of I equal to rho to the power of I pi of 0. How does it happen? You can just unroll this. So pi of 1 equal to rho pi of 0, then pi of 2 will be rho of pi 1, then pi of 3 will be rho of pi rho into pi of 2, etc. Okay. So essentially you will get this. You will get something like this, pi 1 equal to rho times pi 0, pi 2 will be rho of pi 1, pi 3 will be something like this, pi of 2, etc. So, if you just keep substituting, okay, you put into this, for example, this will be rho times pi okay, rho times pi 0, okay, really rho square pi 0, okay. This will be again same thing, rho pi 2 is rho square pi 0, will be rho cube pi 0, things like that, okay. So, pi 1 is rho pi 0, pi 2 is rho square pi 0, pi 3 is rho cube pi 0, but then the probability should all sum to 1, right. So, that means that rho of pi 0 plus rho of, sorry, okay. So, pi 0 plus pi 1 plus pi, all those things should be equal to, the maximum is n, so we can just, it should be equal to 1, okay. So, so pi of 0 is rho pi 0, sorry, what is this? So, it's pi 0 is common, 1 plus rho 1 plus rho square, etc., equal to 1, okay. So, I think we can add pi of, we assume if you do not have any limit on the number of things, it can be any number, okay. If there is a bound, then we have to solve it more carefully, but if it is no bound on the q, it will go to, it can go all the way. So, pi 0 will be equal to, from this you can say pi 0, what is happening, pi 0 equal to 1 by 1 plus rho square plus etc. This is basically 1 by, what is this, equal to 1 minus 1 by rho. This is basically equal to 1 by 1 minus rho. Did I make a mistake? Pi 0 plus pi 1 second pi 0, 1 plus rho, okay, yeah. So, what is this, 1 plus rho square etc., it is going to be equal to 1 by 1 minus rho, right. So, it is going to be 1 minus rho, okay. That is basically what you get, and therefore, that says 1 minus rho, that is pi 0, okay. So, pi of I is equal to 1 minus rho to the power of I, okay. And you can also compute mean number of customers. How will you find the mean number of customers? Again, by, let us say, the probability of 0 guys being there is pi of 0 multiplied by 0 plus the probability of being with only one customer is 1 multiplied by 1, okay, pi of 2 into 2 etc. And pi of 0 is what? It is pi 0 into 0 is 0, that's gone, sorry, and pi 1 is rho of pi 0, which is 1 by rho into 1 minus rho plus 2 into rho square 1 minus rho etc., 3 rho cube 1 minus rho etc., okay. And if you calculate this, this is S. So, again if you multiply by rho is equal to rho square 1 minus rho plus 2 rho square rho cube minus 1 minus rho etc. So, again 1 minus rho is equal to rho 1 minus rho, okay, plus this will be rho square 1 minus rho plus rho cube 1 minus rho etc., okay. Now, this can be summed up. If you sum up all these things, because this is basically a geometric progression and you can compute S from here, okay. It's very straightforward manipulation. If you compute that, you will find that the mean number of customers is rho 1 minus rho, okay, rho by 1 minus rho. You can see that if rho becomes close to 1, the mean number of customers starts going to infinity, okay. So, rho should never be close to 1. One of the most important things that you have to do in a system design is ensure that your utilization, rho is utilization, is not close to 1. It should be closer to 60% or 75%. Do not ever try to get to 90% etc., okay. You will start seeing big queues developing at that time. Okay. And so the expected waiting time is basically this is the number of customers and this is the rate at which you are processing them, the service rate. Okay. So basically E of n by mu. If you talk about service time, it will be not only the waiting time plus also your own service time, that is E of w plus 1 by mu. Okay. This is the waiting time because other people are already in front of you, and this is your own service time. Okay. So 1 by mu minus lambda. Again you can see that if mu and lambda are very close and mu being greater than lambda, you are going to have very high service time. Okay. So you should again try to ensure that the service rate is much better than the arrival rate. Okay. So basic thing is that the reason why queues develop at all in the first place is because even if you are in the situation where service rate is higher than arrival rate, is because of the stochasticity in the system, and some queues will build up here and there, but they will get flushed out fairly soon. Okay. On average you will be in a stable situation, but you can have imbalances here and there now and then. Okay. So if it turns out, if you do this MM1, that is how we did MM1 here. So now if you take the response time for separate queues, right, this is basically this one, 1 by expected service time is 1 by mu minus lambda, that is what I am putting here. Okay. It is this is same as that, 1 by mu minus mu into rho is basically lambda. Okay. Now if rho is equal to, now the situation right now is what is rho for the separate queues. If you remember this, remember that there is for separate queues, right, you have lambda by, here I have set 4, but actually I am doing mm2 there. Okay. So it is lambda by 2. So the actual rate at which things are coming is lambda 2 for mm2. This mm4, therefore I divided by 4 here to make sure that the rate same for everybody. Okay. But if I am using mm2, then lambda 2 will be there. Okay. So you will see that rho will be same as the new lambda by 2, which is half of the other configuration divided by mu, because the service rate is still the same CPUs are there. Okay. So E by W is basically the same as this, 1 by mu minus rho. You substitute mu minus rho of this one, you will get this 2 by 2 mu minus lambda, and then if you just for comparison with the next one I am coming, I will multiply this with 2 mu minus plus lambda on top and bottom. That is, so I will get 4 mu. Basically I am multiplying the bottom by 2 mu plus lambda and 2 mu plus lambda on both numerator and denominator. So that if I multiply the top by 2 mu plus lambda, 2 times will give this, and bottom will come 2 mu minus lambda into 2 mu plus lambda, that will become 4 mu square minus lambda square. Now I am not going into this MM2, but it turns out you can do something similar. E of n will turns out to be this much, and EW going to be this. It turns out that it will be 4 mu times 4 mu square minus lambda square. You will see that the waiting time for 4 separate queues is similar to this. Okay, 4 mu, but the 2 lambda is there here, but it is not there here. The 4 same thing, everything 4 mu square, everything is same. Okay, so you can see that this has to be in every single possible case, this has to be bigger than this, unless lambda is 0. Of course, if lambda is 0, you do not have anything to talk about, right. So what this is showing is that if you do this kind of analysis, you will be able to say that MM2 is better than MM1. MM2 is better than 2 of MM1. That is what it is showing. Similarly, in the what I said before, 4 of MM1 is not as good as MM4. And what is it saying? It is basically saying that put all your processing power in a single large capacity kind of system. Do not split it up into pieces. You split it into pieces, basically what happens is that sometimes there are shortfalls, sometimes there is over this thing, and you can't manage it as well. Whereas if you have very large capacity, then it can process things so fast. Therefore, even if there is a momentary imbalance, it can cope up with it very fast. Whereas if you split up the processing power, when there is a sudden momentary balance, it will take longer time to fix it. Okay. So this is basically the intuition behind why you will see that you want to combine, have a larger kind of memories, okay, larger kinds of let us say CPUs, etc., which you want to put in front of for processing, and that large amount usually takes care of those momentary imbalances quite well compared to split up resources. Okay, we will just also look at some, just like Little's laws, there are a few other types of laws which are quite useful. These are called utilization laws. Okay. Again, these are, you can see they can be done with basically simple algebra here. What is utilization? It is nothing more than busy time by time, okay, the time taken. Okay. So, how much of the time you are busy by the total time. So, what is this? You can as well write it as completions by time into busy time by completion. Basically, I am introducing these completions. You can see this completion and this completion cancel, right? It is nothing more than busy time by t itself. Okay. But if you look at completions by time, what is that? It is a throughput. How many things I complete in a particular time? That is throughput. And what is busy time by completions? It is basically service time. Okay. There I am busy so much, and I took this number of completions I did. That means this I am busy for every single thing. I am busy. That is the amount of service time. Okay. So, and this is true for any device in the system. It could be a disk, whatever. Okay. So, at device I, utilization is throughput I into service time. Okay. This is a thing you can derive. Okay. Similarly, there is something called forced flow law. Okay. What is it saying? Essentially, it is saying that if the throughput of the whole system is capital X, system throughput, okay, that drives rest of the system. See, there is a bottleneck device that determines the throughput of the whole system, okay, because that bottleneck device drives the whole throughput of the whole system. Now, everybody is going to be affected by that particular rate at which the bottleneck device is driving the whole system. So, everybody else has to be corresponding to that, and that is what this is saying. Okay. Again, let us look at it. What is forced flow law? Device throughput of device I is completions of I by t. Okay. At a particular device, I do so many completions, so many times I do something, and I am taking so much time t. Again, you can write it as completions of I divided by completion of jobs into completion of jobs by t. Same, like this completion of jobs can be cancelled. This is A by B into B by C. That is what I am doing. Okay. Completions of I divided by completion job. So, this is cancel, this and this to cancel. So, basically it is actually completions of I by t, same as this. But if you say completions of I by completions of jobs, what is it? This is basically the number of times I am coming to this device to get my job done. It is basically visit ratio. See, this is the number of times. What is completions of jobs? How many times I finished a job. But completions of I is how many times I finished doing some job, I did something for a job. How many times I have done it at device I? Okay. So, this is basically the visit ratio. That is how many times, if I want to get some job done, how many times I go to a particular device. Okay. That is what this visit ratio is. Okay. For example, if you are going to a government office and you have to talk to some person 10 times, okay, before your job is done, that visit ratio is 10. Okay. So, again, what is completion jobs by t? That is nothing more than system throughput. So, that is why this is what is called forced flow law. Basically, your device throughput or device I is given by the visit ratio multiplied by the throughput. Okay. So, essentially what it is saying is that the system throughput forces how things happen at each particular device with respect to its throughput. Okay. If your system throughput is high, then you are not a bottleneck device, then your thing will correspond to that same system throughput, how many times you are. Okay. For example, if I increase the some throughput of a particular system, correspondingly everybody else in the system also has to somehow correspondingly increase also their ability to process things. Okay. That is basically what it is. You can also have utilization of device. Okay. Now, utilization of a device is basically this one, right? What we said, utilization is what? Throughput into service time. That is what he said. Now, but throughput is what we decided here is XVI. Okay, that basically throughput is same as visit ratio into system throughput. So, it is basically visit ratio into system throughput into service time. So, I am just combining these two equations. first I start with this throughput into service time, but throughput is given by this, so I put visit ratio and system throughput here. Now I can see this, I can take out system throughput, visit ratio into service time. Okay, I multiply, because it's visit ratio into system throughput and service time, but if I multiply visit ratio I into service time, that is basically the total service demand and service. That is, I visit a device visit ratio number of times, every time I ask for Swiss amount of time at the device. So visit ratio I into service time is basically total service demand on device. Okay. So the utilization is decided by the total demand on the device multiplied by the throughput of the system itself, X. So these are three types of utilization loss. Okay. So we have Little's loss and we have these things, and these are usually similar to the back of the envelope calculations. Okay. And these are slightly better than that one. Okay. Back of the envelope calculations sometimes can create, they might not work out as well as some of these rules. Okay. There will be some situations where you will find this kind of rules quite useful, and storage systems typically many of the things you can actually, if there are bottlenecks, okay, they can drive the system. Okay. And just let's take a example. Suppose there is a program which requires 5 seconds of CPU time, and for getting that program completely done it requires 80 hour requests to disk A and 100 hour requests to disk B. That is, has to go so many times, it has to go to disk A to get something done. Okay. Disk A takes 50 milliseconds, disk B takes 30 milliseconds. Okay. There are lot of terminals like your access terminals with so many, with disks A throughput is 15.7 hour request. I have taken this example from a book. Okay. And average think time is 18 seconds, because people are sitting in front of a terminal before they issue a request, they typically take 18 seconds before they make a request. The question is, what is the system throughput? Okay. So let's so basically what can we say from this program, from this particular problem? Is saying that we have to visit disk A 80 times. So visit ratio for disk A is 80 and visit ratio for disk B is 100. So what is the total demand on the disk A? What is the demand? We looked at demand, right? Demand is basically, we want to find the total service of on demand. Okay. Okay. We want to find the total service demand on device side. That's basically one. So it's basically visit A multiplied by service time. What is service time for disk A? 50 milliseconds, 1 by 20th of a second. So the total demand for disk A is 4 seconds. Similarly, total demand for disk B is going to be the number of times you visit the disk multiplied by the amount of service time required in disk B. Now it is 30 milliseconds, it is 3 by 100, that is 3 seconds. Now you already know that disk A throughput has been given 15.7 hour requests per second. Somebody has observed it, okay, that it is doing 15.7 hour requests per second. Okay. So that is basically the system throughput X of A. That is same as because of the force flow law, right? You say X of I equal to X of X into Vi. So X VA. So now you know VA because that's the number of times you go to disk. So you can see that the system throughput is basically X equal to, from this, 15.7 by 80. That is the number, that is the throughput of the whole system. So essentially it's doing about, it's taking about this amount of, basically you are able to achieve a throughput given by this. Okay. Similarly, if you look at the CPU, right, it says it takes 5 seconds of CPU time. Now what is the visits to CPU? The basic idea is that the assumption is that your program requires 80 hour requests and 100 hour requests. That means it has to do something, then go to disk, and do something, go to disk, or A, B, etc. That means it has to keep visiting those things. Okay. So again it has to, once it has finished the disk activity, it has to go back to CPU again. Alright. So it's going to do, number of visits to CPU will be given by number of times it goes into disk and come back to CPU again. It has to be rescheduled again back to the CPU. So the number of visits is going to be number of times it goes to disk A, number of times it goes to disk B, and the last time it does it and goes out. So 181. Okay. And now you will notice that the utilization of CPU is going to be given by the throughput of the system multiplied by the total demand in the system. Okay. Again it comes back from the same thing, utilization device, because the CPU also is like a device. Okay. So you know already X, and you know the demand on the CPU which is 5 seconds. So therefore, you can see utilization 98%. Okay, that's what is the system throughput we have calculated. Device utilization. You can also compute a device utilization of disk A and disk B, given that X is there and you know the total demand also. Okay, so you can make this kind of calculations. Okay, you can see from here that we have been able to figure out that the utilization of the CPU is 98%. Now this is very high. That means that if you are really trying to improve the performance of the system, you better find a way of putting a much faster CPU, because at 98%, remember the utilization is what? What is utilization? The disk. Oh, sorry, because I'm okay. Utilization is this part. Is basically lambda by mu. Okay, so you are in a situation where your response time is going to be proportional to 1 by 1 minus rho. So since it's 98%, that means you are going to be, if there are any fluctuations, it can hit you very badly. If things are nicely coming with reasonable things, it will work out well. But suddenly there's fluctuation, there will be a problem. Okay, so I'll skip this part. Okay, but basically the thing is, you can using measuring certain parameters from the system and looking at the way the requests are flowing in the system, you can actually compute some of these details. Okay, but most importantly, you have to remember these utilizations, force flow, and okay. There is a similar thing that we can do. I think I will skip this part. I will talk about the bottleneck analysis. Okay, okay, we'll do this also. Okay, so what is basically this is the number of Q is the number of things in the system. Okay, so basically at device 1 there are Q1 guys waiting, Q2 guys waiting at device 2, Qn guys. The total number of guys in the system is Q. Now we from the Little's law, the number of guys waiting in the system is Q. Okay, so that is same as throughput in the system multiplied response time. Okay, and this is same as all the guys waiting, sigma of Q1. Now this is per device, so you can essentially per device we know what Qi is, right? It's basically Xi into Ra multiplied by R. Okay, right? So again this is we are using Little's law again one more time, and so basically you will look at R into sigma of this R into Xi becomes the number of visits. So essentially you will find that Q is equal to sigma of Vi Ri. Okay, what it is saying is that if you look at the number of visits at a particular device multiplied by the response, you sum up all of those things, that will tell you how big the how many people are there in the system. Okay, I am just using Little's law to derive this, and we are using this Qi equal to Xi Ri. Okay. Okay, again this basically we are using Little's law one more time. Okay, and there are some systems for which you have interactive systems that think time is given, and basically if think time is Z and the response is R, in time t you can only make t by Z plus R requests. Okay, because you have to add your think time and response, and that's the number of times you can go back and ask for some service. This is the maximum you can do. Okay, again with n users what happens? Now the n of these guys, they can all make n into t. Okay, and divided by t is because that's the total time you are thinking about. So essentially this is the system throughput is given by this, which is n by Z plus R equal to X. Again response time is now therefore given by n by X minus Z. Okay, so this is one, if you have interactive system, this will be useful that way. Okay, now if you want to do bottleneck analysis, basically if you have a bottleneck device, the throughput of the system is decided by the bottleneck device, and then that has got a maximum demand of service. Okay, basically that bottleneck device has got a lot of visits or whatever it is, and that's causing the system to be driving the system to what it can do. Okay, so but the utilization is always less than or equal to 1. So that's why X should be always less than 1 by D max. So if there is a bottleneck device, it is going to satisfy this property. Okay, we already seen this one. Okay, right. So the guy with the largest demand, okay, is the thing who is going to set the stage for everybody else. So, since utilization cannot be more than 1, therefore, x has to be less than or equal to 1 by d max. Okay. Now, that is why your throughput of the system will definitely be equal to or less than this guy. There is one more parameter which comes from interactive thing. Basically, if you take only one job, there are no queues, right, because only one job. Therefore, the service demand is basically the demand of at each station. So, that is d1 plus etc. to d. Whereas, if I have n jobs, the response time has to be certainly more than the response time for a single guy, okay, that is d, which is d. So, x of n is basically n by using this particular thing, n by this r of n plus z, and r of n is basically greater than d. So, it is basically less than or equal to n by d plus z. That is why you get this min on this. Okay. Therefore, if you do this bottleneck analysis, you can say that you look at the bottleneck device and look at its demand, total demand, how many times some guy is asking for service, how many times is visiting that guy, see how much time it takes, that is total demand. And that guy will essentially set the stage, or if there is from the interactive response time, okay, this guy will also can be the limiting factor. Between the two things, they will actually limit what is possible in the system. Okay. So, you can do some simple analysis of this kind, and you can essentially get some very good insight into the system. Okay. Luckily, you can see there is nothing complicated here, everything is very simple algebra, okay, extremely simple algebra, okay, and this is good for storage kind of systems, because there is one guy who is really slow, and that guy drives everything else. That is in some sense you might call it the bottleneck guy. Okay. Okay. The minute everybody is about the same speed, then you need more complicated models. Okay. But so far storage systems have been slow, so that is why you can do a lot of back of the envelope calculations. Okay. Okay, so I just want to conclude here by saying that do simple models, probably you get some insight. If that insight does not work with what you see, then you try to come with slight mode. Always start with simple things first. Okay, that is all I have to say.